Joining us now is Julia Greer with the California Institute of Technology. And Julia, you were presented with a Kavli Early Career Award in Nanoscience. Congratulations to you.
Thank you so much.
You are more than welcome. So tell us about your talk titled Three-Dimensional Architected Nanostructured Metamaterials.
It's a mouthful, isn't it?
It is. And you said your talk's about an hour long?
Yeah, so I'm going to try to compress the hour-long talk into this, couple of minutes that we have here. Yeah, so what we make are these very intricate three-dimensional nanolattices, if you will, which don't have to be periodic, but some of them happen to be periodic, where the sizes of the individual unit cells within these lattices are smaller than what your eye can discern. So when you look at it, it looks like a cloud sitting on your hand, but it's very strong, and you can't really tear it apart, and it's very, very lightweight. And so the reason why we call them, we can break them apart, the reason why we call them metamaterials is because the lattice elements within the structure are close enough in dimensions to the characteristic length scale within the material. And so it's this intricate interplay between the material properties, which are at the nanoscale, so nano materials, and the specific atomic makeup, which is the microstructure in the materials, and the dimensions of the overall, and the geometry of the overall structure. So it's the combination of the architecture, the nanomaterials, and the microstructure together that give rise to these very interesting properties, which are not expected, which are surprising in many ways, and this is in part why we call them metamaterials.
Well, you did it in about 30 seconds.
Yes.
Good job. All right, your work has applications obviously across a number of important fields, including biomedical devices, lightweight batteries, and more. So tell us about some of the practical uses.
Sure. So these nanolattices can be made out of just about any material class. So we've made them out of semiconductors, we've made them out of metals, we've made them out of ceramics, and especially relevant for biomedical applications, we can make them out of biodegradable or biocompatible materials. So if you're thinking of an implantable biomedical device, if we could make them directly, say, out of titanium or out of silicon, we can implant it directly in the body, and for the most part, they won't biofoul. So that means that the body, the cells won't attack it, won't reject them. That's not something that we're producing already, but that is certainly a promising way forward as we're making these in our lab. These are research biomedical devices, but as we implant them into maybe not real humans at this point yet, but what we're studying is the cell behavior. And what we're learning is that we can control the cell behavior either to enhance their affinity for the nanolattices or to take it away. And so from that, we're hoping that once we start making the real devices out of them, we can implant them in the body and they won't get attacked.
That's amazing.
For example.
So that's the future, obviously, but what are some of the challenges that need to be overcome for something like that?
Yeah, right now it's the scalability. Right now we can make very small amounts of them in very small structures. For example, the nano trusses that we've been making, maybe the largest one would be something like 0.5 centimeter by 0.5 centimeter by about 100 microns thick, which is the thickness of a sheet of paper. So they're little coupons, and of course you can hold it in your hand, but you don't want to know how long it took us to write it. So it's a long process to write each one of these, and so we're really aggressively pursuing ways to scale these up. And by scaling them up, I don't necessarily mean making very large amounts of it, but instead making a large number of small devices, because their applications, like we said, was lightweight battery electrodes and biomedical applications. Not only, we're working with doctors from UCSF and from the City of Hope, so we can make better materials that are both biocompatible and lightweight and mechanically robust. So it turns out there are so many real world problems in the biomedical field that require materials like that that right now are not being used.
You're going to be busy for a long time. You're giving some talks here, but what are some other talks that you're looking forward to at the 2014 MRS Fall Meeting?
So I'm really interested in the scalability issue, like I said, for how do we take these materials, new architectured materials, and then take them from the benchtop in the lab towards mass production. So there were some tutorials here on roll-to-roll processing. How do you process something where you can achieve very high throughput but yet in a complex type of a material? And so I'm particularly interested in, say, roll-to-roll processing and maybe biomimicking and in self-assembly types of the talks in this conference.
Now, we've been talking science, obviously, but let's talk the arts. You are an accomplished pianist. Do you find there's any correlation between your love and affinity and obviously you're good at the arts with also the science aspect of your life? Is there any correlation there?
Yeah, absolutely. Playing the piano is something that I do every day. So I practice at midnight to 1 every day.
Wow.
It's both. Actually, it's the creative part of it. Absolutely, it frees your mind. It allows you to really be creative. It allows you to be spontaneous. It allows you not to comprise yourself into this little box. You know, stick yourself into this little box. And this cliche phrase that's called, you know, thinking outside the box.
Outside the box.
Thinking outside the box is no problem when you're practicing, but it also gives you the discipline. It gives you this ability to basically say, you know, whatever I'm at, doesn't matter. I'm going to go practice piano because this is my art. This is what I do right now. And so you kind of free yourself from the constraints of the daily lives and this sort of tossing. I call it tossing and turning in your mind.
Right.
You know, when you go
can
and practice,
lose yourself.
you lose yourself. You let go, and you come out a better scientist on the other side.
Very good. Julia, thanks so much.
Thank you so
Enjoy
much.
the meeting.
Yeah,
it was
thank
great
you.
to meet you.
Great to meet you too.
And if you'd like to hear more from Dr. Greer, her talk is being recorded and will be available several weeks after the meeting at mrs.org/on-demand.